As I said, I live in Brussels. You see it clearly. It is the middle of the Europe. I'm a systems architect. My customers are usually from the transportation area, from logistics, or from medical devices. And as you said, I am an organizer of IT meetups in my home village. And working as software architect, I did realize a couple of years ago that as a software architecture is being considered as a technical field, but we operate in a more complex socio-technical environment where we have to deal with social and technical aspects. And that made me realize that we have to rethink the role of software architecture at all. And I started to think about the definition of what the software architecture or systems architecture could look like. And to answer this growing complexity of socio-technical work of systems architects. And after reading a lot of definitions of system architecture, I found out the one which was the more appealing to this reality, which is systems architecture would be the navigation of complexity in projects. And I would visualize the role of a systems architect as someone who writes the curve of the residual uncertainty, because the complexity comes from uncertainty, and the role of a systems architect would be to write this curve of residual uncertainty and to understand the sources of the uncertainty. And if an architect faces some discussions about, some technical discussions, for example, about the database technology, he or she would say, okay, guys, this topic is very important, but it is not on the curve of the residual uncertainty for now. And the goal or the mission of the architect would be to understand what are the current topics to be placed on this curve of uncertainty. And while writing this curve of the residual uncertainty, I was trying to understand what are the sources of the uncertainty and complexity. And after some thinking, I've developed this quadrant with 4 different sources. First of all, the technical uncertainty. So this is a classical uncertainty that we as architects are already familiar about, where we have to hedge technical options under the given risks. But there are also different other sources of uncertainty. For example, the domain uncertainty, where we start to develop a project without fully understanding the domain, or operational uncertainty, where we have to plan something without knowing how much time or cost will it take, or even the political uncertainty, where in any organization, political tensions emerge from the interests conflicts of different agents. And for sure, there are already some proper established methods that try to bridge different sources of uncertainty. For example, domain-driven design bridges technical and domain uncertainty, or team topologies or org topologies or unfix try to bridge technical uncertainty with operational uncertainty. But as of today, I don't know any approach which addresses all these 4 sources of uncertainty that we face in reality. And that makes kind of the discrepancy between what the systems architecture can offer today and what is expected from it today. And based on this discrepancy, I was trying to figure out a new holistic approach that really addresses these 4 sources, 4 dimensions of uncertainty, to make the navigation of complexity in software projects easier. And the idea that I want to share with you today is very, very simple. Basically, socio-technical systems like software projects, where we have social structures like people and teams, and technical structures like the software we produce, they are very complex. But at the end, they are systems, and we can approach them like any other systems. For example, like for any other systems, we have different phases or different aspects of systems engineering. We have requirements engineering. You see this here on the left picture, the biblical code given Moses, the 10 testaments, commandments as a requirements documentation or specification. After that, we have design phase. You see here the biblical code designing a human being, or you see here on the right the troubleshooting, which we do for the normal systems as well, but we can do it also for the socio-technical systems. You see here this great flood, where as a biblical God have seen, okay, I've created the humanity, but they didn't perform well. I have to troubleshoot it, so I will reset everything by sending this great flood. And by this approach or this mindset, I would define socio-technical engineering basically as classical systems engineering, which is very common, applied to socio-technical systems, which are basically our software organizations, software projects, and so on. And in today's talk, I will just guide you through these three aspects of systems engineering, but applied to socio-technical systems. But first of all, small disclaimer, I don't see socio-technical engineering as a method. It is rather an approach to think about socio-technical systems or mindset. And within this mindset, within this approach, you can use multiple methods: Scrum, SAFe, domain-driven design, team topologies, so whatever you like. Socio-technical engineering is just a way of thinking of socio-technical systems as classical systems. So let's start with requirements. As you know, for technical systems, we have functional and non-functional requirements, and we can also define functional and non-functional requirements for socio-technical systems. Let's start with functional requirements. They're quite obvious. For example, the project X should develop the product Y. It sounds very straightforward, but it also is loaded with a lot of information, useful information. For example, it means that the project should just build the product Y, but nothing else. Or it also means that the project X have to build a lot of artifacts with the product Y. It's not only the software, it is also some requirement documentation, it is a test plan, it is maybe a project handbook. And this list of technical artifacts will help to guide both technical and organizational decisions, because if we know the list of these artifacts, we know which roles do we need, and we know which people we have to hire to fulfill these roles to deliver this set of artifacts. This requirement is very simple and obvious, but it showcases the role of requirements because they can help navigating design decisions. We have also other examples. For example, like if you want to sink costs by 40%, it is usually positioned as organizational requirement, but it is actually a socio-technical requirement because we have to make some changes in our social architecture of organization and both in technical organization of the systems and artifacts we create. Another example, we want to build a platform for other products. It's also a socio-technical requirement because one thing is to build a technical product, the technical project platform, but other thing is to make changes in the organization structure so that other teams and departments will use this platform. So this were functional requirements, and as with technical systems, there are also non-functional ones, like availability or development availability. One can specify a requirement like we want to be able to make any technical decision without relying on a single person for approval. Maybe you are familiar with a situation where someone says, oh, we can't make this decision because lead architect or the project lead is on vacation. So this was a case where the development was not available because of the vacation of the single worker that is able to make decisions. And it is not bad or good, and absolutely, the question is what requirements you have. So this requirement clearly conflicts with another requirement, making a project lead, for example, efficient. The question is not what is bad, what is good, but which requirements you have. And making these requirements transparently will have to guide the technical and social decisions. Another example is development scalability, where one might say, okay, we want our organization to be able to increase productivity by hiring more people. But as the experience shows, often what happens is that more people gets hired and the organizations becomes even less performant because the technical architecture is not prepared for it. And having requirements like this will help for sure social and technical architects anticipate those changes and prepare architecture, both social and technical one, for requirements like this. So this was about requirements. So basically, requirements have to navigate both social and technical decisions. They also help to reduce complexity and navigate social and technical discussions. They also help to verify the system design against the set of requirements, because if we don't have requirements, we don't know how to verify our socio-technical system. Now, having requirements in place, we can go to the next chapter, which is design. And the idea here is very simple. Basically, design of any system is making arrangement decisions about systems elements. And if we understand what are the system elements in socio-technical systems, and what are the arrangement decisions in socio-technical systems, then we get a language to describe our socio-technical design. And with the help of this language, we can express our design, we can communicate it, and we can discuss it. And afterwards, we can even use tactics and design patterns for solving structurally similar requirements in other systems to fulfill also our functional or non-functional requirements. So let's go through these three aspects of system design. First of all, system elements. So what are the system elements in socio-technical systems? One can answer this question by looking on what happens in software projects. In software projects, people work on artifacts according to their roles. Basically, we can visualize this on this entity relationships diagram. We have persons, people, we have roles, and we have artifacts. The roles are allocated to people, people work on artifacts, and other roles could be stakeholders of artifacts. For example, Cassandra is a person, and the role of lead architect is allocated to Cassandra. So it's like allocating some service to a worker instance. And we could define the role of lead architect as responsibility for software architecture documentation. So basically in this notation, the role is not defined by what the person on who the role is located is expected to do. The role is just defined as a responsibility for certain technical artifact. And we could also say that the role of software engineer is a stakeholder of the artifact software architecture documentation. And what one can do in software projects to draw the socio-technical system design, one can play this role and artifacts mapping by showcasing what artifacts does the system have. For example, in the middle, you see here artifact software architecture documentation, which role you have in the project. For example, here software architect, somewhere here product owner, and so on, and which people you have in the project. For example, here Eva, Chris, and Kate. And then you can look whom we allocate the roles, like here the product owner role is allocated to Kate, or which roles are allocated as responsibilities for artifacts. For example, software architect is responsible for software architecture documentation. And one can draw this infinitely big, large diagrams to showcase the dependencies and relationships in the project. Because following this diagram, one can say, okay, Kate is a product owner. We know that product owner is a stakeholder of this artifact, and this artifact is held responsible by the role software architect, and the role is allocated to Cassandra, which basically means that Kate can go to Cassandra and express her information needs so that Cassandra knows what to put in the software architecture documentation. So basically, these diagrams can help people to get in touch and understand what are the information needs of each other. So these were elements. Another part of this design language would be design decisions, arrangement decisions. So first of all, we have decomposition decisions. For example, you want to split project organization into teams, or you want to split the system into subsystems, into subcomponents. This is the first type of this first kind of arrangement decisions. After you split it, the question is how to integrate it. For example, how to integrate two teams. Should they have some Scrum of Scrums, or some weekly, or just a Slack channel to integrate their work? Or should two components be integrated by middleware or database or synchronous communication and so on? And the third type of arrangement decisions is allocation. As we saw previously, to whom we allocate the role of lead architect, or where do we want to allocate the component X? Should it be allocated on an edge device like smartphone, or should it be allocated in the cloud? So these are the examples of allocation decisions. And with the help of system elements and arrangement decisions, we can now express the socio-technical design of any socio-technical system. We can verify it, comparing it to the set of requirements. We can discuss it with other people, we can communicate it, and so on. But what we also can do is to use patterns and tactics from other systems to fulfill similar requirements. So it is basically the classical biomimicry where we use in technical design the patterns we see in the nature. Here's an example how it could work. Let's go back to our availability requirement. If we want to be able to make any technical decision without depending on anyone, if this is our requirement, what we can do is to look into the catalogs of available patterns and tactics for availability. For example, in this book, Software Architecture and Practice, you can find nearly 30 tactics to address availability requirements. For sure, not every tactic is applicable for your use case, but you can use these catalogs as checklists for inspiration. I will just pick a couple of them to see how we can approach our availability requirement. First of all is the redundant spare, where we just say, okay, we have one role and we allocate it to 2 persons, which basically means that every one of these persons will be not so efficient as it would be if it would be the single worker instance, because 2 persons have to sync with each other on the daily architectural stuff. But this reduction in the performance will ultimately lead to the increase of the socio-technical availability of the role lead architect. Another idea would be to use a combination of 2 tactics, self-test and the removal from service, where we just will remove one service component from service and see what happens. What we can even do is to write BDD-style tests for it, like given the allocated lead software architect is on vacation, when an external software architecture audit for the project is requested, the audit should not result in any major findings. So what we can do, we send Cassandra on vacation or just wait until she goes on vacation and then request the audit and see how the audit results. And then we have either green or red test case, and if it's red, we can change the system design to address this issue. So this was design, basically like for technical systems. If we have a language of elements and decisions, we can express design, we can verify it, and we can reuse other patterns and tactics from other domains to fulfill our own requirements. And the last part of this talk is about troubleshooting, because like any other system, socio-technical systems might have bugs, and we have to fix them. For sure, there is no universal solution to fix all bugs and all systems, but what we can do is to follow generic principles of troubleshooting. And the first is that the bugs are relative. If we don't have requirements, then there are no bugs. For example, if someone complains we have too many technical bugs, and if there is no requirement on quality of the software, then it's works as designed. Maybe the requirement was to deliver something very quickly. It's no wonder there are so many bugs. The same is if someone complains that one has too many meetings, maybe it works as designed. If there were a requirement to have distributed remote teams, then it is clear that they would need to meet often and align on their work. So it might work as designed. And the conclusion here is that there is a difference between bugs which relate to requirements and perceived bugs, which are just something not going as expected. And in order to make perceived bugs to real bugs, one has to change requirements and maybe change design. Anyway, if you want to make these bugs as proper bugs, we have to create new requirements to navigate the solution. Another idea would be that in complex systems, it doesn't make sense to solve problems, because as Russell Ackoff, it was a complexity scientist, said that in complex systems you have messes as systems of interconnected problems. And these messes, they basically generate problems. And instead of solving problems, because problems are just symptoms, one has to resolve messes that generates those problems. And we can apply this mindset also for socio-technical systems. For example, let's take the meetings problem. If a project has too many meetings, then it doesn't make any sense to make the meetings more efficient. Like there are common policies. Let's allow people decline meetings if they have nothing to contribute, or one can make meetings more efficient by appointing a moderator, or one can cluster all meetings in the first part of the day, because it makes the meetings more efficient, but it will not solve the mess which creates the meetings. And if you want to understand what is the mess that creates so many meetings, we have to look into the socio-technical architecture of the system, socio-technical system, which could be that there are two teams in the projects. One team is responsible for one component, another one for another one. These two components have fetch dependencies, which results in two teams having meetings over those because neither of the teams can make any decisions on their own. And so this is basically the mess that generates so many meetings. And one can dissolve this mess by bringing two technical components into one and making team A being responsible for this new big component, and the team B is now free. They can go and eat ice cream. Anyway, the meetings problem will be dissolved. So basically, that's it. As I said, the socio-technical engineering is nothing else but systems engineering for socio-technical systems. And with this approach, you can write requirements for socio-technical systems, you can design them, and you can troubleshoot them like any other systems. You can also apply this approach in practice. For example, in your organization, you can run socio-technical engineering workshop where you will understand the context of the socio-technical system. So what is within the system, what is outside of it, which people are inside, which are outside, which artifacts are inside, which are outside. Then one can gather requirements, as we've seen, functional, non-functional ones. One can document design, socio-technical design, by applying, for example, roles and artifacts mapping. And if there are already some existing messes in project, one can dissolve them by following the two generic ideas I've presented today. So if you are interested in socio-technical engineering, I just started to write a book on it on LeanPub. It's just the beginning, but I will publish the progress on LinkedIn and my website, complexitynavigator.rocks. If you're interested in the topic, I would be very glad to stay in touch and exchange ideas with you. Thank you very much. And